Start by reading the question. A student wanted to excite a ground state, that's n equals 1, hydrogen atom to an electronically excited state with n equals 3 and L equals 1. So the transition we're looking at is an electron absorbing energy and moving from the n equals 1 state to the n equals 3 state. The fact that L equals 1 is irrelevant in this case, since in a one-electron system, anything with the same principal quantum number n has the same energy. They used a laser light that emits at a wavelength of 355 nanometers, but were not successful. Explain. The next step is to plan your approach to solving the question. If we determine the wavelength that would be required to induce this transition, we can compare it to the wavelength used by the student in the question. To find the wavelength, we can use the Rydberg equation. But first we have to rearrange it to solve for wavelength. The Rydberg constant, RH, is 1.097 times 10 to the 7 inverse meters. So before we finish, we'll have to convert our answer to nanometers using the proper conversion. Now we can move on to solving the question. Substitute in the values for the Rydberg constant and the values for n1 and n2. Remember, n2 should always be greater than n1. Then calculate the answer. Now we can convert into nanometers. Make sure your units cancel. This tells us that the wavelength required to excite an electron from the ground state of a hydrogen atom to the n equals 3 excited state is 102.6 nanometers. Finally, we need to explain the observation in the question. Write, the wavelength must be 102.6 nanometers or shorter, so 355 nanometers is too long to induce the transition. Now before you move on to the next question, check your work. Have you used the right units? Have you included the right number of significant figures? Does your answer seem reasonable? If so, you're done.